All right, continuing on, we now look at regression estimation. As with ratio estimation, we will assume that we have two variables, y and x, available for measurement, with population means mu sub y and mu sub x, respectively. Ratio estimation is appropriate when mu sub y and mu sub x are proportional, that is, when they are linearly related and the line passes through the origin. If the relationship between the means is linear but does not pass through the origin, then regression estimation will be more appropriate than ratio estimation. A model leading to such a situation is of the form as follows: y equal to alpha plus beta times x plus epsilon, where both alpha and beta are non-zero. Under this model, the population means are related according to the linear relationship mu sub y equal to alpha plus beta times mu sub x, where the y-intercept, alpha, is non-zero, and so therefore this line does not pass through the origin. So you'll recognize this statistical model as the model for the simple linear regression line. Now, the regression estimator of mu sub y is given by the following formula. Mu hat sub y is equal to y bar plus b times the difference between mu sub x and x bar. And again, I see I have a y hat here. That should be a y bar, so that's just the average value of the y's. Now, the value b is equal to the ratio of s sub xy divided by s sub xx. We looked at those quantities at the very beginning of the semester when we looked at descriptive statistics or summary statistics, but I've provided the equations for s sub xy and s sub xx here on the bottom of this slide. S sub xy is the corrected sum of products for the x's and the y's. S sub xx is the corrected sum of squared for the x's. Right? And so the ratio of those values gives the estimated slope coefficient, which we're denoting by b in this formulation. Now, the estimated variance of the sampling distribution of the point estimator, mu hat sub y, is given by the following formula. Cap n times little n over cap n times 1 over little n times 1 over little n minus 2 times the difference between the corrected sum of squares of the y values, s sub yy, minus b squared times s sub xx, the corrected sum of squared of the x's. So s sub xx was given on the previous slide. S sub yy is given on the bottom of this slide. And so once we have that estimator of the variance of mu hat sub y, we can take its square root to get the estimated standard error of mu hat sub y. And so that's just the square root of that quantity on the previous slide. Once we have that, we can multiply it by 2 to get the approximate 95% margin of error associated with mu hat sub y. All right, so that's just 2 times sigma hat sub mu hat sub y. And then once we have both the point estimator, mu hat sub y, and its approximate 95% margin of error, we could use those together to come up with an approximate 95% confidence interval estimate for mu sub y. So mu hat sub y minus plus the estimated margin of error, which again is given by that expression on the slide. All right, so let's look at an example. This is example 7, regression estimation of mu sub y. A mathematics achievement test was given to 486 students prior to their entering a certain college. From these students, a simple random sample of n equal to 10 students was selected and their progress in calculus observed. Final calculus grades were then reported as given on the following slide. Now, it is known that mu sub x is equal to 52 for this population of 486 students taking the achievement test. So in other words, for all 486 students, we know all of their scores, or it could be that we don't know all the values for everybody, but we do know the average, the population average of mu sub x. Now for the sample, okay, here are the values for the sample that we have. So Y is the final calculus grade, X is the achievement test score, and as always, the corresponding X and Y values are paired. So the 39 goes with the 65, the 43 goes with the 78, and so forth. And so we are to use the data to estimate mu sub Y, the mean final calculus grade for the entire population of students, compute the margin of error associated with this estimate, and in addition construct an approximate 95% confidence interval estimate of mu sub Y, the mean final calculus score for the entire population of students. All right, so the population size is 486 students. The sample size is 10 students. We have the following summary statistics. The sum of the x's is 460. The sum of the squared x values is 23,634. The sum of the y values, the calculus scores, is 760. The sum of the squared y values is 59,816. The sum of the x's times the y's is 36,854. Now, from the summary statistics, we can calculate the corrected sum of squares for the x's, s sub xx, and also the corrected sum of squares for the y's, s sub yy. Right? And so using the expansion formulas, the shortcut formulas for each of those, we get a value of 2474 for s sub xx, and for s sub yy we get 2056. We can also calculate the corrected sum of products for the x's and the y's, the s sub xy, and using its expansion formula or shortcut formula we get 1,894. Now the estimate of the slope coefficient, which we're denoting by b, is equal to the ratio of s sub xy to s sub xx, and that turns out to be 0.76556. Y bar, the mean of the calculus scores for the sample of students, is 76. X bar, the mean of the achievement scores for the sample of students, is 46. And we're given that mu sub x, the population mean score for the achievement scores for all 486 students, is 52. All right, and so using that information, the regression estimator for the average calculus score for all students in the population, so mu hat sub y, again being given by this expression here, turns out to be 80.5934. Now, that's our point estimate. We want to construct an approximate 95% confidence interval estimate for mu sub y as well. And so to do that, we'll first need to calculate the estimated variance of mu hat sub y. All right, so this formula gives us the estimated variance, and that turns out to be 7.4195. The square root of that gives us the estimated standard error of mu hat sub y, which is 2.7239. Multiplying that by 2 gives the approximate 95% margin of error associated with mu hat sub y, and so that's 5.448. And then using that in conjunction with the point estimator, mu hat sub y, we get an approximate 95% confidence interval estimate for mu sub y, the average calculus score for all 486 students, as being somewhere between 75.2 and 86.0. So that's how we can use regression estimation to estimate the mean of a population using another concomitant variable and its mean, mu sub x, to come up with more precise estimator of a population mean. And so we have really two techniques here in this particular module that allow us to do this: ratio estimation and regression estimation. Again, ratio estimation is appropriate when a linear relationship exists between two variables and that line, that linear relationship, goes through the origin. All right, so that is equivalent to a proportionality type of relationship. Regression estimation is appropriate when there's a linear relationship between two variables, but that linear relationship does not go through the origin. All right, and so if there is a linear relationship between two variables and it does not go through the origin, then ratio estimation would really not be the appropriate technique to use. Regression estimation would be the better choice. So that wraps up this particular lecture and the module on ratio and regression estimation. We'll continue on in the next lecture video with the next module.